got a worksheet. We're going to do some problems on, we're just going to get some practice with finding and classifying relative extrema. I've chosen a set of problems that kind of works through a lot of the different algebra things that can come up when we're trying to solve for finding those relative extrema and then classifying them. For our partial with respect to x, I think I'm looking at 2x plus 6y. And for the partial with respect to y, I think I'm gonna get 6x plus 20y minus 4. How'd I do on my partials? Matching up? So I'm setting both of those equal to 0. Now, in terms of solving this, I could certainly graph those. I'm probably not going to. But both of these are lines, which means the solution to that system should be either a single point or an infinite number of points or no points at all. And if I've done this correctly ahead of time, we should get to a single point. I'm going to choose probably to maybe multiply the first equation by 3, subtract the second equation from it. Not the only option, but using our elimination skills from 19b, I think I'm going to get 0x, 18 minus 20 would be negative 2y, 0 minus negative 4 would make that plus 4, and I'm getting that y is equal to 2. And if y is equal to 2, I'm going to choose to plug that into my top equation. So that means 2x plus 12 would need to be 0. So I get that x is negative 6. For some of the problems that you're going to encounter on the web work, for some of the problems you're going to encounter in real life, there might be some sort of restriction on the feasible domain. Because we don't have any context for what x and y represent, I'm not bothered by the fact that we got a negative number. And for the web work problems that are just like a function, and then we're finding and classifying the relative extrema, we don't have to worry about if we get negative numbers or not. So here, the only critical point that we've found is negative 6, comma 2, comma, and we would have to plug the negative 6 and the 2 into the original function to come up with that z value. I'm going to skip that piece for right now. Now, in terms of classifying, if we go backward in time to 19a, we could have looked at the concavity, or we could have done a first derivative test and like put things on a number line to see where we're increasing and decreasing. There is no three-dimensional equivalent of that sort of first derivative test. But we do have a second derivative test, and that is to take a look at the value of the Hessian. Now, let's kind of look at this equation for a second. This part of it to me kind of makes sense because this part is the most directly related to our second derivative test from 19a. If I'm concave up in both the x direction and the y direction, then I must have been at a minimum. If I'm concave up in one direction and concave down in the other direction, this term will be negative. And that's what's happening if I'm at one of those saddle points, where I'm concave down, concave up. The bonus piece of this is essentially what Grant likes to call the twist. So we can have some sort of weird things happening in 3 dimensions if our mixed partial derivative has more of an influence on what's going on than our second derivative or concavity does. So if we're at a place where our concavity is really, really flat, then the mixed partial derivatives have more of an influence on what's going on. So overall, if our value of the Hessian is less than 0, then we're going to be at a saddle point. And that's either going to happen because our concavities are mixed, or we're really flat and this sort of twist term is influencing what's happening. When our Hessian is positive, we're either at a max or a min. And we're going to determine that based on looking at the concavity, based on looking at our partials with respect to x and our partials twice with respect to y. So for this particular problem, did you already do the partial derivatives? They're pretty friendly for this one. Oh, so our textbook calls it the Hessian. So it calls it the Hessian. So I was rolling with the language of the Hessian. The connection back to the determinant is from putting this into a matrix of partial derivatives, where I have my second partial with respect to x twice, my partial first with respect to x and then with respect to y, my partial with respect to y and then with respect to x, and my second partial with respect to y twice. So the Hessian is the name given to the determinant of this second partial matrix. So if I do these second partial derivatives, they should be pretty simple for this problem. So with respect to x twice, starting here, I'm now at 2. With respect to x, then y, I get 6, which for all of the functions that we're going to work with in 19C, these two should be equivalent. Some weird things can happen out there in the universe in non-conservative fields where these two things would not be equivalent. If I look at the partial with respect to y twice, looks like we're getting 20. Is that what you all got also? So if I look at the value of the Hessian there, I've got 2 times 20 minus 6 squared. So 40 minus 36. This works out to be positive. And then if I look at my concavity in the x and y direction, they're both concave up. So I must have been at a relative minimum. This is not at all representative of what this thing looks like in 3D. That was just me going, oh, it's concave up in both directions. So very, very close to our critical point, it's going to look like a little cup that's concave up in both directions. But the overall picture of the graph, I have this, it looks like for fixed values of z, that should work out to be the equation of an ellipse, but this is not in the scope of something you would be asked to graph at all. I will go ahead and get caught up on my first partial derivatives at least. Maybe not sure right, sorry. Are my first partial derivatives matching what you've got? So one of the things to note here, when we set these equal to 0, conveniently, that top one factors, and that's really our fastest path forward through the algebra part. So the top one factors, and I can pull out a 6x, and then I'm left with 2 minus y if I do that, which means that solutions to my partial with respect to x look like x equals 0 or y equals 2. One thing to note, 0, 2 is not a critical point. Or it might be, but I don't know that it is yet. And the reason for that is both of these are solutions to my partial with respect to x being equal to 0. But in order to be a critical point, I also need that partial with respect to y to be 0. So factoring it now means I can kind of play out the scenario, what if x is equal to 0? And then play out the scenario, what if y is equal to 2? So if I play out x equals 0, down here in my partial with respect to y, then this becomes 12y minus 3y squared is equal to 0. And that, I can now pull out a 3y and have 4 minus y is 0. That has now given me 2 critical points. X could be 0, y could be 0 for matching up with the 3y part, or x could be 0 and y could be 4. Then I can play out the scenario, what if y was equal to 2? And if y were equal to 2, and I look at my partial with respect to y, 2 times 12, so that's 24, minus 3x squared, minus 2 squared is 4, 4 times 3 is 12. So now I've got that would be equal to 0. So 12 minus 3x squared is 0. I can pull out a 3. I'm going to be left with 4 minus x squared, which means this is giving me 2 critical points. X could be positive 2 while y is positive 2, or x could be negative 2 while y is positive 2. So now I've got 4 possible critical points to play with. So if I construct my matrix of second derivatives, you think I can squeeze it in and keep it on screen? So if I build my matrix of second partial derivatives, if I start with fx and I take the derivative with respect to x a second time, I've got 12 minus 6y. If I take that derivative, but now with respect to y, I've got negative 6x. If I start with my partial with respect to y, I take the derivative a second time, but with respect to x, I get negative 6x, which is good. We should match. And now if I take my partial with respect to x, I get negative 6, sorry, with respect to y. Cool, I got this. With respect to y, I'm going to have 12 minus 6y. I want to point out that it is a not exactly a coincidence. I chose the problem, so it's not really a coincidence. But in general, these partial derivatives don't need to match up. It's just the mixed ones. It just so happens that I chose a function where the second partial with respect to x and the second partial with respect to y happen to be the same. So when we're at 0, 0, this would look like 12 times 12 minus 0 squared. That is definitely positive. And both of my second derivatives are positive. So I know that means we're concave up. And this is a relative min. At 0, 0. Oh, we can plug in 0. If I plug in 0 for x and y, this one conveniently is 0. If we look at the Hessian at, where are my other points? Oops. So 0, 4. So if I look at 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, 0, 4, When I plug in 4, 6 times 4 is 24. So 12 minus 24, I would have negative 12 times another negative 12 minus 0 because my x is still 0. This is positive. This time, both of those concavity pieces are negative, which means I'm concave down, and I've got a relative max at 0, 4, and if I plug that in to get the z value, f of 0, 4, I'm going to skip all my x pieces, so that's 6 times 4 squared minus 4 cubed. And then if we check our Hessian at our other two critical points, -2, +2. So this time when I look at my, oh, okay, so why is 0, 4 a relative maximum? Again, I'm not drawing the entire graph. I'm just looking at what's happening on the graph very, very near that critical point. These are both telling me about the concavity. So that's telling me that I'm concave down in the x direction, and I'm also concave down in the y direction. So very near that critical point, whatever else is happening, I know that I had to be at a relative maximum.
So positive, negative is not like when you do multiple f(x) and f(y), but like interest.
So right. So first we look at the overall Hessian, right, which is the determinant of this matrix. So I can either use the matrix or the formula. They're interchangeable, but we're looking at, so like first step is overall, does that overall formula give us a positive or a negative? And if that overall formula gives us a positive, then we need to look at the concavities. If the overall formula gives us a negative number, we already know we're at a saddle point. 2, 2. So when I plug in 2 for y, my fxx is 0 and my fyy is 0. So this is 0 times 0 minus, when I plug in -2 here, that'll become a positive 12 squared, and overall this is negative. So I know that I'm at a saddle. And this is what I was talking about when I said that extra piece on the end, looking at the mixed partial derivatives, that really comes into play when I'm very flat. So when my concavity in the x direction and my concavity in the y direction are both nearly 0, or in this case, actually 0, that's when this mixed partial derivative really influences the shape of the graph. One last one to do here, and our Hessian at 2, 2. Same thing's going to happen on my fxx, fyy. This will be a -12 squared, but that's still going to give me a value less than 0, and this is also a saddle. And again, if I were putting this into WebWork, it is important. WebWork is asking you for the point, which means you do have to plug it in and figure out what that z value is. Tackle the algebra part together here. Okay, so as always, make sure I take my partial derivatives correctly here. So my partial with respect to x, I get 12y minus y squared minus 2xy. So far, so good? Okay, I'm gonna leave myself a little bit of space. And my partial with respect to y, I am looking at 12x minus 2xy minus x squared. So if I set the top one equal to 0, what's the only thing I can factor out? And if I do that, I now have 12 minus y minus 2x. And nope, I'm going to write my partial with respect to y over here. Sorry. Just trying to give myself a slightly cleaner page. Okay. On this part of it, the thing I can factor out is an x. Which I think I did okay on those. Okay. From our partial with respect to x, that means one of two things is going to be true. Either y is equal to 0, or if I were to set this other piece equal to 0, I'm going to go ahead and move my y over and say that says 12 minus 2x is equal to y.
Oh.
Well, because what's in parentheses has to be equal to 0, and so I just moved my y over. If I do the same thing with this one, this says that either x is equal to 0 or x is equal to 12 minus 2y. So my 4 critical points come from the 4 ways to match these things up. So either these two things are true at the same time, which gives me the critical point 0, 0. Or these two things are true at the same time, which means I can plug in 0 for y here and get the critical point 12, comma 0.
To be the point on both sides.
Correct. So these are sort of the conditions that came from setting my f of x equal to 0. There's two possible conditions. And from setting my fy equal to 0, there are two possible conditions. And I kind of need one from column A and one from column B. So if I were to match these two up, then that gives me the critical point 0, comma. And so here, if I plug in 0 for x, I get 0, comma 12. And then the one that's going to require a little bit of work is setting the bottom two equal to each other. And if I set the bottom two equal to each other, that's the one where I actually have to solve a system of equations. So now I need to solve 12 minus 2x equals y, and x is equal to 12 minus 2y. And you can solve that system however you feel like. Oh, I'm not really setting them equal to each other. I just need both of them to be true at the same time.
Oh.
Yeah, maybe there's a better way I could
So-
indicate that.
We can-
We need to solve this system. Of this system, I would have 12 minus 2 times 12 minus 2y needs to be equal to y. So 12 minus 24 plus 4 y is equal to y. So negative 12 is equal to negative 3y. So y is equal to 4. And if y is equal to 4, looks like x is also 4. So solving these two pieces equal to each other gives us 4, 4. And now you've got 4 places to check the value of the Hessian. Not saddles. $24.
So maybe a quarter and quarter is not terrible.
Okay. At 4, looks like I'm concave down in both directions. And does it overcome the twist part of it? 12 minus 8 minus another 8. So -4 squared. Yep. I get that we are at a relative maximum at 4. Because we're concave down in both directions. Yeah. Derivatives this time are actually pretty friendly. So when I take the derivative of e to the something, I just get e to the something back. And I only have to remember that chain rule says I need to take the derivative of what's up top. And since it's the partial with respect to x, and I'm adding that y squared, that part's 0, and I'm just going to end up with 2x. When I take the partial with respect to y, almost exactly the same thing is going to happen, but this is going to spit out instead a 2y. Here's really the main point to remember. If I'm setting those equal to 0, e to the something is never equal to 0. So this actually is only giving me the very boring point that x would be 0 and y would be 0. So I actually only need to look at all of those partial derivatives at the point 0, 0. But when we take those second partial derivatives, we will have some product rule going on. So good reminder about product rule. When I take the second partial with respect to x twice, because both of these terms have x's in them, I do have to use product rule here. Derivative of that first piece just pops back out another e to the x squared plus y squared times 2x, and then we'll bring the 2x along for the ride, and then I will leave the first piece alone and take the derivative of 2x, which is 2.
So do you know that the point is 0, 0?
Yeah, I know the point is 0, 0. There isn't any other point that could happen.
Why?
So 0, 0 makes both my first partial with respect to x and the partial with respect to y equal to 0. E to the x squared plus y squared will never be equal to 0.
So the function is just 2x.
Right. So if 2x equals 0, then x is 0. And if 2y is 0, then y is 0. That's kind of the only thing we're matching up.
And then you said like on the page before, you have to check to make sure that that's like those two together are a point.
Mm-hmm.
Like you can't just assume that point is 0. Is that
I can assume it because one of them came from my partial with respect to x and one came from my partial with respect to y. So I think the one that you're looking at or thinking about was the one where from just my partial with respect to x, I got two pieces that factored. That's not a point because they both came from my same partial derivative. Yeah, does that kind of answer? But here, it's actually that I got one piece of information from my partial with respect to x and one from my partial with respect to y. Yeah, and there's nothing that taking the log of both sides would help for that. Really, it's just the fact that e raised to any number is always positive. And if I think about that graph of e to the x, as x approaches negative infinity, we're approaching 0. But I also am never gonna head to an e to a negative number because these are both squared. So for lots of reasons, I don't have to worry about the e part. My partial with respect to y twice looks a whole lot like the partial with respect to x twice. Again, I've got a product rule when I'm doing this one because both terms have y in them. So I'd have e to the x squared plus y squared times 2y. That's just from the partial of this first piece with respect to y. And then the product rule part says I need another 2y. And then I'll have e to the x squared plus y squared times 2. For my partial with respect to x and then y, or the partial with respect to y and then x, either way, I don't have a product rule when I'm doing this. So if I start with my partial with respect to x and I now take it with respect to y, because that 2x is not a function of y, it's just coming along for the ride. So I'm going to have, doesn't matter which order you write these in, but I'm going to have a 2x, an e to the x squared plus y squared, and then a 2y popping out because of the chain rule. And this time, I think I will make my matrix, but I'm already just going to plug in the 0, 0. And as a reminder, e to the 0 is equal to 1. So when I look at my second partial with respect to x twice, if at the point 0, 0, this whole piece is going to go to 0 because I'm multiplying by x. This will be 1 times 2, or 2. If I look at my mixed partial, because I'm at the point 0, 0, that's going to be 0. And when I look at my partial with respect to y twice, that's going to go to 0 because I'm plugging in 0 for y. And this will look like 1 times 2, or 2, which means that my Hessian at 0, 0 is equal to 2 squared minus 0 squared. That is positive. And whenever my Hessian is positive, I'm looking at my concavity. And since both of these are positive, I know that means that very near my critical point, I'm concave up. And this had to be a relative min. And this one is easy enough to plug in the numbers. So I'm going to plug in the numbers. So I've got a relative min at 0, 0, 1.